Hi friend, let's welcome to Engineer Choice channel. Uh, I have already uploaded two, three videos, second and third video. I have completed the basic theory regarding the superstation strain. Now, after a long time, I have started this series again. And in simple station strain, moving forward, we will discuss about the numericals to calculate the elongation and stresses in the basic parts. Okay, so I am planning to upload the videos, all that subjects which are related to structural engineering, like engineering mechanics, strength of material, structural analysis 1, structural analysis 2, then design of RCC structure, reinforced cement concrete structure, and then design of steel structure and the process concrete structure. So to upload that videos, I request you please like and subscribe my channel so I will get motivate from you to upload such kind of videos. So the main motivation of videos is just to share my knowledge to you, and if you have any query, please write your question in the comment box. Okay, so I will definitely answer to every questions. And now I have just started the strength of material. Similarly, in the upcoming days I will upload the videos which are related to other in structural subjects, okay, which are related to the structural subjects. So I request everyone, please subscribe my channel and like this video, and watch this video up to the end. So this video is related to the numericals as I have discussed, and generally I have divided all these topics. We will discuss it in uh, next slide. So list of content, these are the contents that discussed in the previous videos. So I will give link of that previous video in the comment box. So please go and watch that videos, because to solve the numerical we must know the basic theory related to that numerical. Okay, so these are the topics that I have covered in the previous video. This is the syllabus that I have considered for the stress and strain unit. So this video is mainly related to the numerical of simple stress and strain. So in the simple stress and strain, I have considered two types of numericals. Okay, the first numerical, the first part is the numerical on stresses and change in length or the deformation calculation. So in first part we will consider only the stresses and the change in length calculation. Okay, and the second part is related to numerical on uniaxial, biaxial, triaxial stress system with E, K and G, where E, K and G, what is E, K and G, that already I have discussed in the basic part. Just go through that videos. So the first, if we consider the first part of stresses, so numerical on stresses and change in length calculation. So I have divided this first part in the sub six parts. Okay. So the first part in that is the first part is general numerical on elongation and stresses. General numerical, in that we will discuss the elongation and stresses. Then second part is the elongation of uniform cross sections bars with the intermediate axial load. Uniform cross section bar. Uniform cross section bar means the dimension of that bar is same from first point to another point. Let's say suppose this is A first point and this is B second point. So whatever dimensions we are considering from first to last, that dimensions are uniform, means same. Okay, and some intermediate forces are acting in that. So that part is called as a, or that types of numerical is called as a uniform cross section pass with the intermediate axial load. Similarly, the third part I have considered, that is varying cross sections bars with the intermediate axial load. Again, intermediate axial load is there, but the cross section of that bar is different. Cross sections are different. Okay, maybe here at the start point and at the end point, the dimensions are different. Okay, so this is the third part. And intermediate axial force is there, obviously, that we will see in upcoming videos. Then fourth is the elongation and stresses in bars uniformly tapering section. Uniformly tapering section means like this. Okay, uniformly tapering section, that is the circular section. Okay, so diameters are different. Fifth one is the again elongation and stresses in the bars of uniformly tapering section, but which section? Rectangular section. Okay, so for rectangular and for cross sections, I have considered the two separate numericals. The elongation and stresses in the intermediate structure. Intermediate structure means suppose some structures are fixed at one end and free at another end, or fixed at both ends. Such type of numericals we will cover in the sixth part. So I am planning to upload all the videos in a different part. So today's topic is related to general numericals on elongation of stresses that we discussed. Okay. Now next, the types of numerical. Types of numerical means whatever numerical we are covering in the first part or in this video. So these are the important formulae as per my point of view. That is change in length. Okay. Delta L means change in length. PL by AE, where P is the axial force or the any force that we are applied on the body. L is the length of that section or the body. A is the area of section, and E is the modulus of elasticity. Okay, so already we have derived that formula in the first third video. Okay, so just go to that video. You can see the all the theoretical parts, all the formulas, whatever formulae I have given over here, five formulas are there. All formulas we have discussed in the last videos. Okay, then again change in length, sigma into L by E, where we know that sigma is what? Sigma means stress is P by A. Okay, stress is P by A. So just we have convert this P by A into sigma. So that is additional formula for this is delta L P, delta L is equals to sigma L by E. Then again sometimes we have to calculate the modulus of elasticity, E. So just we have convert this E. Okay, and we have derived or we have considered another formula, that is PL divided by A into delta L. Third, ultimate stress. Okay, while calculating ultimate stress, we have to consider the load at yield point divided by cross section area at the yielding point. So basically we know that stress is equals to P by A, but sometimes we have to calculate the stresses at the different level. Already we have discussed the stress variation in the stress strain curve diagram, initial point, final point, yielding upper yielding point, lower yielding point, ultimate point, that already we have discussed in the stress strain curve. So whatever points are there on the stress strain curve, so we have to calculate that stresses in the different point. So whatever basic formula we are considering for the stress is the P by A, and if you want to calculate the ultimate stress, so for ultimate stress your uh, point load or the P is at a ultimate point and A is the cross sectional area. That area will not change, but force will change where you require the stresses or as per the stresses you require. Suppose you want to calculate the yielding stress at upper point, so the yielding force at upper point divided by the cross sectional area, that will be the formula. As per the your convenient you can convert that formula, that we will see in upcoming videos. Then percentage of elongation, so how much bar is elongate. So that types of numericals is also coming in the syllabus. So we are calculating that percentage, and the formula for the calculation of percentage is delta L by L into 100. Then percentage reduction in area. So suppose if we are applying the tensile force on the any material or on the body, so that material will get elongate. So due to that elongation, how much percent that body or that material is elongate, that you can calculate by using this formula, fourth formula. And some in sometimes or the every times the area of that particular sections will reduce. Okay, so how much percent in which percent that area get reduced, that we can calculate. That is reduction in area divided by total area. Spelling reduction in area. Okay, reduction in area divided by total area, we will see one by one. So as per my point of view, these formulas, five formulas, are most important for today's lecture. So let's start with the general numericals on the elongation and stresses. So first numerical is determine the elongation of steel rod of length 900 mm and the cross section 600 mm square, cross section area 600 mm square, subjected to an axial pull of 40 kilonewton. Take E equals to 200 gigapascal for steel. So in this numerical, determine the elongation of steel of rod. Elongation means delta L. We have to calculate the delta L. Rod length of 900 mm. Okay, L is given. Rod length means length is given. Then cross sectional area of that rod is means area is given. Okay, subjected to an axial pull of, axial push means tensile force is given. Okay, that is 40 kilonewton. And the Young's modulus is also given. That Young's modulus is no, sorry, 200 gigapascal. So 200 gigapascal is 200 kilonewton per mm square. So unit conversion already I have discussed in previous video. So please visit that video. Link is in description box. So here we require change in length, and the change in length, and the formula for change in length is PL by AE. Everything is given to us, correct? Everything is given in numerical. So where P is how much? P is 40. Okay. Then L is 900. A is 600 and E is 200. So just put all the values and get the answer. So when we solve this, so we will get 0.3 mm. So change in length is 0.3 mm. So see here, our E is given in kilonewton per mm square. Okay, E is given in kilonewton per mm square. That's why just wait. That's why we no need to change unit of P. Okay, we no need to change the unit of P. But suppose if we require, or if the E is given in Newton per mm square, so in that case we need to convert that P in uh, Newton. So just multiply by 10 to the power 3, you will get is in Newton. So unit conversion I have covered in last video. Okay, now comes to next. So now here we get change in length. So final answer is change in length equals to 0.3 mm. Second numerical, the aluminum rod of length 1200 mm and cross section area 400 mm square is found to elongate by 1.5 mm when subjected to an axial pull of 35 kilonewton. Determine the modulus of elasticity for aluminum. Now see the difference between these two numericals. Here we require change in length, but now here we require the modulus of elasticity E. Again, given data is same, but only, or the formula is same, only given and given data is different, and the output, required output, is different. Okay, so let's see. L is given, aluminum rod having length 1200 mm, cross sectional area A is given 400 mm square, and elongation it's found to elongate by. So change in length is given, that is 1.5 mm, and the axial force pull is 35 kilonewton, and we required modulus of elasticity. So again formula is same, change in length. Okay, change in length PL by E, but now here we require E, so just convert this E, L and E, just change the position of that L. Okay, so P L by A into delta L, where P is 35 kilonewton, L is 200. Just put the all values, you will get answer, and the E is the 70 kilonewton per mm square. So just we have said that 1 gigapascal is equals to 1 kilonewton per mm square. So we can we can general consider kilonewton per mm square is equals to gigapascal. So 70 gigapascal. That is second numerical. Now next, third one, determine the elongation of steel rod of length 100 mm and the cross section area 800 mm square subjected to an axial pull of 50 kilonewton. Take E is equals to 210 gigapascal for steel. Again same elongation we require. Okay, same all values are given. Just put all values, you will get this answer. Okay, same numerical. The next one, steel rod of length 1000 mm and the cross section area 500 mm square is found to elongate by 1.8 mm when subjected to an axial pull-up. Again we required modulus of elasticity, same numerical that we have considered in the second. Okay, just put all the values, you will get the answer. Okay, just take these two numericals for your study. Okay, then next, a hollow steel bar of length 2 meter has a circular cross section of a outer diameter 80 mm and thickness 10 mm. Determine the change in length if it is subjected to an axial pull of 80 kilonewton. Take E equals to 200 gigapascal for steel. Now here some changes are there. See, hollow steel bar of length 2 meter. Okay, so circular cross section is given and the length of that circular cross section is 2 meter, but in numerical or in formula we required the length is in mm, so just convert that length is in mm. So here 1 meter is equals to 10 to the power 3 mm, so just your L is 2 into 10 to the power 3 mm for the requirement of formula. Okay, then next, has a circular cross section of outer diameter 80 mm. Outer diameter is given. Generally we consider outer diameter as a capital D and inner diameter as a small d. So here we are considering outer diameter is 80 mm, so capital D is 80 mm and thickness 10 mm. Thickness is given, correct? T. Let's consider thickness is a 10 mm. Okay. Now determine the change in length. What we require? Change in length, delta L. Okay. If it is subjected to an axial pull of 80 kilonewton, force is given 80 kilonewton, and E is also given. Okay, that is 200 gigapascal, and we know 1 gigapascal equals to 1 kilonewton per mm square. So 200 gigapascal is equals to 200 kilonewton per mm square. Now everything we have calculated, or everything we have considered over here, but one thing is important here. External diameter is given, thickness is given, we need to calculate the internal diameter. So why we require that internal diameter? Because if you see the formula, change in length is equals to PL by AE. PL by AE, where A is what? A is the area of section, and here hollow circular section is given, so we need to calculate the area of that hollow circular sections, and we know the formula to calculate the area of hollow circular section, pi by 4 capital D square minus small d square. That's why we require the small d, means internal diameter. Okay, so how we can calculate the internal diameter? Total diameter minus thickness on both sides, this thickness and this thickness, because this is our total diameter, just minus these two thickness, we will get the internal diameter. That is internal diameter small d equals to 80 minus thickness, that is 60 mm. Okay, now we require area for the calculation of change in length, and the formula for area is pi by 4 capital D square, means outer diameter square minus small diameter square. So once you solve it, we will get the area of that hollow circular section is 2199.11 mm square. Okay, now just put again same method, just put the all values that we have considered in the given data and the calculate change in length. So P is 80, L is 2 into 10 to the power 3, A is 2199.11, that just we have calculated, and the E is 200. So change in length for this circular cross section is 0.3637 mm. That is the final answer. Okay, now next fourth one is the following observations were made during the tensile test on mild steel specimen 30 mm in diameter and the 20 mm long. We know that tensile generally we are considering one test in laboratory, that tensile test on mild steel aluminum, to calculate the actual capacity of elongation of that particular specimen. So this numerical is related to that one. So tensile test is conducted on the mild steel specimen. The diameter of that specimen is a 30 mm, and and 200 mm is long. And these are the observations during the test. First is the load at limit of proportionality 40 kilonewton. The corresponding tension 0.054 mm, yield point load 90 mm, ultimate 90 kilonewton, ultimate load 140 kilonewton. The length of specimen at a fracture is 241 mm. See, I have already discussed in the tensile test we will get the so many points, means upper yield point, lower yield point, initial point, limiting point, then ultimate point. Okay, already we have discussed in the theoretical part. So just at that observations he is getting, means the we are getting these values, means ultimate load, corresponding extensions, means low extensions at the ultimate load, then yielding point load, then ultimate load. Okay, so these are the loads that we get from the test. Okay, so now see one by one. First write down the given data, determine. So what we require here, Young's modulus of elasticity, we have to calculate the Young's modulus of elasticity, yield stress, ultimate stress, and the percentage of elongations that we required or that we need to calculate. Okay, so first diameter is given 30 mm, length is given 200 mm, load at limiting point. Load at limiting point is 40 kilonewton. Let's say modulus of limit elastic limit. Okay, 40 kilonewton. Change in length at that point is 0.054 mm. Yield point load, okay, upper yield point load or lower yield point, whatever, he has not mentioned the which yield point, but at yield point load is 90 kilonewton and ultimate load is 140 kilonewton. Okay, and the fracture length means where that total specimen is get fractured. Okay, that length is 241 kilonewton. I think unit is changed, it's not kilonewton, it is in mm. Okay, now comes so obviously first we need to calculate the area, and the circular section is given, so pi by 4 d square. So the area is 706.86 kilonewton mm, sorry, 706.86 mm square. So first we required ends of modulus, okay, or modulus of elasticity. Again we just convert this formula in E, that is change in length, equals to PL by AE, whatever formula is there, change in length equals to PL by AE, just convert this formula is in E, PL by A into delta M. So all values we have, that is P is, now see all, so many P's are given, forces are given, load at limit, ultimate load, yield point load, and the ultimate load is given. But whatever load, but here we required the modulus of elasticity, so we need to consider the load only within the limit of elasticity, correct? We are not considering load at the yielding point or ultimate point. So for the modulus of elasticity we are considering load at the limiting point. So 40 into L is 200 mm. Okay, then area and just elongation at that point is given. At the elastic limit the elongation is 0.054 mm, so just put all values, we will get that answer, modulus of elasticity 209.58 kilonewton per mm square. Okay, that first answer we got over here. Second, we required yield stress. Okay, this is our given data. Yield stress. The formula for yield stress is general formula is what P by A. But now here we required stress at yield point. So we need to consider the forces at yield point. Correct? Only that difference is there. So the force at yield point is how much? 90 kilonewton. Correct. So just consider 90 kilonewton. 90 into 10 to the power 3. So 5 here we have converted that kilonewton to newton, that is 10 to the power 3, because stress is in newton per mm square. Correct. Stress is in newton per mm square. So just convert your 90 kilonewton is in newton. So 10 multiply by 10 to the power 3. Area is 706.86. So we will get that answer 127.32 Newton per mm square. Okay, this is our final answer. Now next we require ultimate stress. Okay, again same stress formula is P by A, but now for calculating ultimate stress we need to consider the stress at ultimate point, not yielding point, ultimate point. Okay, ultimate point. So the load at ultimate point is given, that is 140 kilonewton. Okay, just put all these load. Correct, 140 kilo, 140 into 10 to the power 3, convert it in newton. Okay, 198.06 newton per mm square, and that is 198.06 megapascal. Again unit conversion, please visit or go to the last video. Then percentage elongation. Okay, so for percentage elongation, the change in length, how much that length has been changed after the test, that we first need to calculate. So initial length is given. See, initial length is 200 mm, and the length at fracture, means when that material get fracture, at that time the length is 241. So how much that material, the specimen has elongated? 41 mm. Okay, so this is a change in length as per our numerical. This is our change in length. Correct. So original length is 200. Correct. Original length is 200. The percentage of elongation, the formula for percentage of elongation is what? Change in length divided by original length into 100. So change in length is how much? 41. That's just we have calculated over here, and original length is 200 into 100. So 20.5% is the total percentage of elongation. Correct. Now next, a mild steel bar of 25 mm diameter and 200 mm gauge length has an extension of 0.15 mm under a maximum load of 75 kilonewton. The load at elastic limit is 160 kilonewton and the maximum load is 250 kilonewton. Total extension is 55 mm. The diameter at fracture is 18.5 mm. See, in previous numerical, length at fracture has been given, but now here diameter at fracture is given. Numerical type is different. So consider the all types of numerical in one video. So if you go all these numericals, okay, okay. So first, elastic limit stress, we require modulus of elasticity, percentage of elongation, and the percentage of reduction in area. Okay, the whatever given, so just write down all the given data over here. First, diameter is given 25 mm. Okay, then length is given 200 mm. Change in length, extension means change in length. Okay, extension means change in length, that is 0.15 mm. P force, axial force is given 75 kilonewton. Elastic limit, the load at the elastic limit is 160 kilonewton. Maximum load is 250 kilonewton. Maximum load is 250 kilonewton. Total extension is 55 mm. Total extension is 55 mm is given. Means we can see the change in length directly given. And diameter at fracture is 18.5 mm. So first we required modulus of elasticity. Correct. So elastic limit stress. Okay. Sorry. First we required elastic limit stress. So formula for stress is again P by A, but here we need to consider force at the elastic limit. Okay, that is 160 kilonewton. Area is 25, sorry, diameter is 25. Then just calculate the area from the diameter, that is 490.87 mm square. So just put these two values in the stress formula, we will get the stress, that is 325.95 Newton per mm square, that is in megapascal. Okay, first we calculate stress equals to 325.95 megapascal. Second thing, we require Young's modulus. Okay, the formula for Young's modulus, we will derive it from the change in length formula, that is change in length equals to PL by AE. So modulus of elasticity E equals to PL by A into delta L. All values are with us, correct? Load, now here we required Young's modulus, so need to consider P, that is at elastic limit 75 kilonewton. 75 L 200, area just we have calculated, and change in length is also given. Okay, 0.15. So just put all the values, we, we will get modulus of elasticity, correct? That is gigapascal, 203.72 gigapascal. Percentage of elongation, see, in previous numerical they have given the total length at fracture, but now here they have given the final extension at the fracture, means total length or the change in length at the fracture, that is 25 mm, 55 mm. Okay, so just put all the values, because formula is change in length divided by original length. The change in length is given 55 mm, original length is 200. We will get percentage of elongation, that is 27.5. Okay, that is third. Fourth one is the percentage reduction in area. So see, for percentage of reduction in area, formula is what? Reduced area divided by original area. Correct? Reduced area divided by original area. So how we can calculate the reduced area? Total area minus area after fracture. Correct? Or area at fracture. So diameter at the fracture is given, that is 18.5. So just reduce the total area from fracture area. So here total area minus fracture area. So total area, for the total area calculations consider diameter, total diameter, and for fracture area consider diameter at fracture. So pi by 4 25 square minus pi by 4 18.5 square. So we will get the reduced area is 222.07 mm square. Okay, so we know the percentage of reduction, that is reduction area divided by total area, again spelling. Okay, percentage of reduction is 222.07 and the total area is 490.87. So percentage of reduction is 45.27 24 45.24%, and the percentage of reduction in area is 45.24. Thank you. So please, if you like this video, please subscribe my channel, that is Civil Engineer's Choice, and like this video, and if you have any query, please comment in comment box. Thank you.